Okay, thank you very much for the invitation to speak here. Should I turn this off? Okay, so I'm going to be discussing a recent paper with Yiming Chen, Haifeng Tang, and Zhenbin Yang. So in Euclidean gravity, with positive cosmological constant, there's this very simple solution of the d-sphere, so the space-time d-sphere. And of course, this is just the imaginary time continuation or Euclidean signature continuation of de Sitter space-time. And if you would like to try to start thinking about Euclidean quantum gravity path integrals in de Sitter space or cosmology, this seems like a nice starting point to try to understand this. So at zero loop order, the Euclidean gravity path integral, of course, it's not really a path integral of this order, gives this answer, e to the de Sitter entropy, e to the area of the horizon divided by 4 g Newton. And that looks nice. It sort of suggests some kind of state counting interpretation where we associate e to the area states to the de Sitter horizon. But the one-loop determinant has this puzzling phase that was computed by Polchinski. The one-loop determinant is proportional to I to the d plus 2, where d is the space-time dimension. So there's been some recent work trying to understand this puzzling phase, and our paper is a follow-up to that work. Here's the plan of the talk. We're going to start by reviewing Polchinski's computation of the phase. The right column here indicates kind of the phase of the path integral at different stages during the talk. So we're going to review first Polchinski's computation that gives this thing. Then we'll review Wan's proposal, which changes the phase to this I cubed. Then we'll discuss a new computation in our paper that gives the same answer using a charged black hole. We'll discuss a little bit the significance of that, and then we'll compute the phase of the density of states. And why this should be different from that will also be explained. Will be explained later. Okay. Yeah, that's the nice thing about Wan's paper is that it's independent of d. So, right. Okay, so the integral of a wrong sign Gaussian can be defined by Wick rotation to give either plus or minus I. So let's start with this divergent integral, which you sort of implicitly imagine as being done along the real axis where it's divergent. Then we can rotate the contour. We can rotate it either clockwise or counterclockwise. And we're going to rotate it clockwise. And that results in this expression. After a change of variables x equals is, we get this integral, which is minus I. If you rotated the contour the other way, you would have got plus I. Whether it's plus or minus is not super important, but it's important to pick a consistent convention. We're going to pick this convention. Okay. So in Euclidean gravity, the conformal factor of the metric, that is like the trace part, which parameterizes fluctuations in the conformal factor, is mostly wrong sign as a field. It's mostly a wrong sign field. In particular, the kinetic term has the wrong sign. So that means that it, as a field, it contains an infinite number of these wrong sign Gaussians. And so if we Wick rotate that in order to define the integral, we get an infinite number of factors of minus I. Now, most of these factors can be absorbed into a redefinition of the measure. So what we mean by this is we introduce some red i's. These are the ones that we insert into the measure. And we introduce one per space-time point. So the measure is an integral, functional integral over metrics. We define it as a product over space-time points of an integral over the components of the metric, but with one factor of I. That's designed so that that one factor of I can absorb one Wick rotation per spacetime point, which is just enough to allow us to Wick rotate the conformal factor. Okay. So this prescription gives a nice real positive one-loop determinant if the action for the conformal factor is completely negative. So if we do indeed get one factor of minus I per spacetime point, then it will cancel this one and everything will be real and positive. Okay. However, now we finally get to Polchinski's computation. For the D sphere, the conformal factor is not negative definite. There's actually one positive mode. That corresponds to the overall size of the sphere. So it's a zero mode of the conformal factor on the sphere, just scaling the whole thing up or down. And there are also D+1 pure gauge zero modes. So what is the implication of that? Well, the phase of the partition function, I should have said, yeah, I'm going to use this squiggly symbol everywhere in the talk to mean has the same phase as. We're only really going to be concerned with the phase. So let's look at the right-hand side. So we have an infinite number of factors of I that comes from the measure. We have an infinite number of factors of minus I, but really it's infinity minus a finite set. So this represents the number of modes that do not need to be Wick rotated. And so the product of those two things is I to the D+2. Now this looks a little bit suspicious because we are canceling infinities. But this infinity is really designed to cancel that infinity because it's one I per spacetime point. So it's the factor that we get for Wick rotating an entire field. Okay. So now let's review Wan's proposal. So let's suppose that we include, in addition to the quantum gravity degrees of freedom on the sphere, we include a observer. I think Wan was motivated a little bit by recent works emphasizing the importance of an observer for understanding quantum properties of de Sitter space. But let's just include it following a great circle geodesic like this. So it's a massive particle following that geodesic. Now, fluctuations around this trajectory have D-1 negative modes. Let me try to, I'm sure you can guess. You just take this circle and you slip it off the sphere a little bit so that it's a smaller circle here. That decreases the length, and so it's a negative mode. And if you do this for the D sphere, there's D-1. So if we combine Polchinski's answer for the gravitational part of the one-loop determinant with D-1 new negative modes, we get minus I to D-1. The total phase is I cubed. And in particular, the factors of the space-time dimension cancel out. Okay, so going from this computation to the density of states introduces one further factor of plus or minus I. And that we'll come back to at the end of the talk. In Wan's paper, he also suggested that you could replace the particle observer by a small charged black hole. It's maybe a little bit more native to the gravitational theory. And we'll follow this suggestion in the next part of the talk. Okay, so your first attempt to replace, to design a black hole as a model of an observer might be to use a small uncharged black hole. But that thing is not in equilibrium with the de Sitter horizon. Its temperature would be high, and so the Euclidean geometry would not be smooth. That would actually be okay. We would be able to do this analysis in that case, but to avoid complications, it's convenient to cool the black hole down by giving it some charge. And if you adjust the charge and the mass of the black hole right, you can make it so that the black hole and the de Sitter horizon are in thermal equilibrium. So that's what we're going to do. Okay, so right, so we're going to use Einstein-Maxwell theory of the positive cosmological constant. It's this theory here. And it has charged black hole solutions. We're going to consider the magnetic ones, although it doesn't make much difference. This is what the solution looks like in Lorentzian signature. So the factor f of r depends on two parameters. Q is the charge. It's proportional to an integer. And the mass m is another parameter. And the mass m can be in some range that depends on the charge. It's allowed to inhabit some range. So that range is described by this plot here. This is called the shark fin diagram. I've drawn it, I guess, the wrong way. This looks like a shark that is swimming downwards. But I like to have the charge on the x-axis, so that's the way we're going to draw it. So the shaded region is the allowed region. And so let's describe the top and bottom boundaries. The top boundary up here, these are what are called the Nariai black holes, or charged Nariai black holes. That's when the black hole horizon gets very big and gets as big as the de Sitter horizon. At the opposite extreme, at the bottom of the gray shaded region, there's this dashed line, and that's when the black hole, what's called the cold black hole limit, where the inner and outer horizon of the black hole coincide. It's like an extremal black hole. Okay, so these are all valid Lorentzian solutions, but it's only these codimension 1 regions where the black hole horizon and the de Sitter horizon are in thermal equilibrium. So it consists of two branches. There's the charged Nariai branch, which I just described. That's when the two horizons coincide. And there's this other branch called the lukewarm branch. That's the more intuitive one. That's like you take a kind of small black hole and give it a little bit of charge to cool it down until it has the right temperature to agree with to be in equilibrium with the de Sitter horizon. And these two branches intersect at this point here that we'll come back to later. There's another special point, the ultra cold point, when all three horizons coincide, and we'll also discuss that a little bit more later. Okay. So these are our smooth Euclidean solutions everywhere along these black lines. And in principle, what one wants to do is compute the full one-loop determinant of gravity around these smooth Euclidean solutions. And that's actually been done for the charged Nariai branch by Ivo and Sun. Their paper came out just after our paper. And this lukewarm one is some work in progress. Okay, we didn't do that. We did something lazier. What we did is we just computed the one-loop determinant within a two-dimensional dilaton gravity theory that you get by doing an S2 reduction. So that is a much simpler problem. And we don't prove that the phase that you get from this determinant equals the phase that you get from the full higher dimensional problem. But we think it does because we believe all the subtle modes are two-dimensional modes. And that suspicion has now been confirmed for the Nariai branch. Okay, so, well, whatever. That's what we're going to study for the next couple of slides. So what is it? We have a space. We described this de Sitter black hole, Euclidean geometry, as a S2 fibration over some two-dimensional base space. The size of the fiber is determined by phi. And if we extract a factor of phi from the base space metric, then we just get this, the Einstein-Hilbert action becomes this dilaton gravity action with a particular potential u of phi that I'm not going to write down. It depends on the charge. Okay, so we can take this action. It has these Euclidean solutions, the lukewarm and the Nariai, and we can expand around one of those solutions. It's convenient to work in conformal gauge, so we have two fields to deal with. There's the dilaton, a fluctuation of the dilaton, that's this var phi. And then there's the conformal factor relative to the classical solution, that's omega. And you can work out the quadratic action. It's some 2x2 differential operator acting on the space of phi and omega. This is the explicit operator. And it has infinitely many positive and negative eigenvalues. You can see that very clearly by kind of taking this operator and looking at it in the UV, where we drop everything except for the derivatives. And then it looks like a Pauli X matrix tensor Laplacian, and that will have an infinite number of positive and negative eigenvalues. Okay. So what we want to do is we want to compute the phase of the one-loop determinant. That means we want to make sense of this product. I to the number of space-time points from the measure comes minus I to the number of negative eigenvalues. And they're both infinite. And for this case, it's not as easy to compare the infinities to each other because we don't have a single field that we need to Wick rotate. The negative eigenvalues are somehow mixed up between omega and phi. And we have in principle, some infinite list of negative eigenvalues and compute their eigenvectors, but it's not very clear exactly how to cancel them against the number of space-time points. So one approach would be to start somewhere where you know what the phase is. So compared to some existing computation for the uncharged Nariai black hole. And then gradually change the charge or the charge in the mass and keep track of eigenvalues crossing zero. So that's one legitimate procedure and it works. You can do that. I'm going to explain a more direct approach that gives the same answer because I think it's a little bit more fun. So here's the idea. So to compare these infinities, we need some kind of regulator. And because we define the measure with one factor of I per space-time point, we need to use a position space regulator where the number of space-time points is super well defined. So in other words, some kind of space-time mesh. And there's lots of software for making meshes. You can make quasi-uniform meshes like this one. You can make non-uniform ones like this one. And given some mesh, doesn't matter exactly how you get it, the number of space-time points is well defined. It's just the number of points. And the number of eigenvalues of D is also finite. So you can define a D as a differential operator on this mesh. And then we can just take this two finite numbers and just compute this product. Okay, and then of course you have to check that the answer is robust to refining the mesh or choosing a different kind of mesh and so on. And we also check that it agrees with this procedure on the previous slide, and it agrees with other regulators like a fuzzy sphere regulator. The only thing you cannot do is make the mesh too coarse. So if you make it too coarse, then you can get a different answer. Okay, so here are the results for the phase. Right, so this is the same plot as we had before. I've just colored parts of it blue and red. So everywhere that's blue, the phase is just trivial phase. Z is proportional to 1. That includes the part of the charged Nariai branch. And the rest of it, the phase is I cubed. So that includes the entire lukewarm branch and then the remainder of the charged Nariai branch. Okay, so first of all, we get the same answer as for the observer for the sort of most obvious case where we take a small black hole. And actually, we get the same answers for the observer everywhere along this red curve. That corresponds to the black holes that are in a stable thermal equilibrium with the de Sitter horizon. So if the black hole is in a stable equilibrium, then we get this phase I cubed. The charged Nariai in the blue part of the curve is in an unstable equilibrium with the horizon. And for this two-dimensional reduction, it's like an L equals 1 multiplet of instabilities. The horizons can separate from each other in any of 3 directions. So there's 3 negative modes, which is why the answer here is minus I cubed times the answer here. Okay, and then there's one funny point here. That's where a black hole is neither stable nor unstable. It's marginally stable. And there's a zero mode, a physical zero mode in the one-loop determinant. So the one-loop answer is infinity. Okay. So the conclusion is that the stable black holes give the same answer as the observer, as was predicted in Wan's paper. We can also check this against a kind of fun analytical computation in the ultra-cold limit. So what happens in the ultra-cold limit is the base space gets really big. So it turns into R2 instead of S2. But if you rescale it to a unit size S2, that's this tilde variables, then you get the following action. Q is a perimeter that vanishes in the ultra-cold limit. So you get a simple dilaton gravity action with a quadratic potential. And you can integrate out phi. It's a positive Gaussian, so you can integrate it out without getting any phases. And you end up with this r squared totally negative action. And it's a negative action, so we need to Wick rotate everything, except there are 3 pure gauge zero modes. So we end up with the same answer. Z is proportional to I cubed. Yeah, this action is sort of interesting because notice that as Q goes to 0, that's the ultra-cold limit, there are large fluctuations. So the base S2 is getting really big, but if you rescale it, then it's getting like very floppy. There's large fluctuations in this space. And in the one loop approximation, the partition function vanishes in the ultra-cold limit. It's a little bit like the limit of an extremal black hole in ADS. It would be interesting to understand this better. Okay, that's sort of a parenthetical. Okay, so let's try to understand the meaning of this answer, the partition function proportional to I cubed. So let's forget about everything we've discussed so far and just try to be optimistic, vague people trying to come up with a model of de Sitter space plus a black hole, a toy model. And a toy model that you might think of would be a pair of thermodynamic systems coupled by an integral over their shared inverse temperature. So we have, we integrate over 2 energies, the energy of the black hole, EB, and the energy of the cosmic horizon, EC. And we have e to the entropy for both of them. And a Boltzmann factor weighted by the same beta. And we could imagine the model of de Sitter space with the black hole is just an integral over these 3 variables. Why are we integrating over beta? We're integrating over beta because we're doing quantum gravity and we're integrating over all the geometrical things. And beta is some part of the geometry. So we're integrating over it. Okay, so that's a very vague model for de Sitter space plus a black hole. And you can actually get something like this for the lukewarm black hole in the dilaton gravity reduction. So this is a picture of the base space, 2-dimensional space, where the dilaton and the metric live. And let's imagine that we do the path integral, but we temporarily fix 3 variables. We're going to leave them to the end, do the integral over those things at the end. So the 3 variables are the value of the dilaton at the black hole horizon, the value of the dilaton on the cosmic horizon, and the length of some curve in between, which we specify by saying it's the length at some fixed value of the dilaton. Okay, so then the path integral is the integral over everything else times the integral over these 3 things. And well, we can work out the action at quadratic order. And it looks like this. We have some coupling between beta and the value of the dilaton. And we have Gaussian actions for the dilaton fluctuations at the black hole and cosmic horizons. These parameters, capital C, are sort of like specific heats. I'm going to refer to them as specific heats. And in particular, CB is positive. That's kind of like a normal horizon, black hole horizon. And CC is negative. That's the funny cosmic horizon. Okay, now, so far we don't know the phase of this one loop determinant prime, the integral over everything else. But we can determine it by the following procedure. So let's do the integral over phi and beta. First, we'll do the integral over phi. So we integrate over phi b and phi c. We get 1 factor of minus I because phi c is a negative mode. And then we get the following final integral over beta. It turns out that CB plus CC, so the sum of the 2 specific heats, is negative. That means that the negative specific heat wins. This total system is has negative specific heat. That means that the integral over beta is convergent on the real axis. So we get minus I times this extra one loop determinant. From our previous discussion, we know that the total answer is I cubed. And that means that this one loop determinant has to be proportional to I to the 4th. So the conclusion of this is that this simple model of 2 thermodynamic systems one with positive specific heat and another with negative specific heat, correctly captures the phase of Z. That's, in some sense, the meaning of this answer I cubed, is that this simple model correctly captures the phase of Z. Up to this factor of I to the fourth that I'll discuss at the end of the talk. Okay. So now let's see how to compute the phase of the density of states. Thanks. So let's remember this integral here. The integral over an inverse Laplace transform contour of beta of this exponential gives a delta function. A very useful application of this formula is when you compute the density of states of some system starting from the partition function. So you do this inverse Laplace transform integral over beta. Now, for a closed universe, yeah, let me make one more comment. So basically what we're doing here is this integral over beta is being used in order to impose this delta function constraint. It's imposing the constraint that E is equal to H, or that H is equal to E. Now, in a closed universe, we don't really compute a density of states per se, but we should impose a constraint that H is equal to 0. And the way to do that, as discussed by these authors, is to integrate the corresponding beta over a similar contour, over an inverse Laplace transform contour. Okay, so just to emphasize the difference, the naive Euclidean gravity path integral would be to integrate over beta from 0 to infinity. Beta is the length of some periodic thing, and the naive idea in Euclidean gravity is you should integrate over real metric. So we would integrate over beta from 0 to infinity. But for the state counting partition function, where we're trying to impose the constraint, we should integrate beta over this type of contour here. Another perspective on this that some of these authors like is that this is like doing a Lorentzian path integral. Beta is the periodicity, and it's like we're making the periodicity Lorentzian instead of Euclidean. And that's a natural way of imposing a constraint. Okay, so that's why there's a difference between the computation of the density of states and the path integrals we've been computing so far. So we need to redo the computation using this new inverse Laplace transform contour. So let's apply this to the lukewarm black hole we've been discussing with this representation that we've been discussing with the 3 variables that we keep to the end. Okay, so our goal is not to do the integral that we did before, but instead to change the contour over beta to this inverse Laplace transform contour. And let's actually do that. So the integral over this delta beta, that imposes a constraint that phi b plus phi c is equal to 0. So that's this delta function here. And the final integral over phi b and phi c reduces to a one-dimensional integral that is convergent because of this inequality between the specific heats, that Cc is negative and it's more negative than Cb is positive. So the final integral here, this thing is real and positive. So the phase of the state counting partition function z count is real and positive. So one comment is that if we forget about this lukewarm black hole discussion and go back to the model of an observer, like this geodesic observer, that reduces to a very similar integral where phi b is replaced by the energy of the observer, phi c is related to the area of the de Sitter horizon. And you come to the same conclusion, exact same conclusion, using this prescription, that in particular, the z count is real and positive. However, there was a little bit of sleight of hand here. And the conclusion that we just arrived at depends on how we define this integral. So I want to emphasize that point. So the next slide is going to have a bunch of equations on it. Some of them are the same equations that were on this slide. So those ones do not count in my equation budget. So we just discussed this computation. I'm just writing it here so you can compare to the next one. Another approach to doing this integral, so notice that we're doing the same integral, same integrand, And same integral. The only difference is that here we're doing the integral in a different order. So in the first, we did the beta integral first. And that was important because the integral we're doing up here is a conditionally convergent integral. In particular, it's convergent if you do the beta integral first. If you don't do the beta integral first, then it's a divergent integral. So the integral over phi c is divergent because this is a wrong sign Gaussian. Remember, cc is negative. But we can rotate the contour. So here we did no contour rotations, but here we're doing the integral in a different order where it's divergent. So we need to do some Wick rotations. And if we Wick rotate phi c, we get one factor of minus I, as we already discussed. And then we get this integral. And remember that the sum of these two things is negative. You probably don't remember, but, well, sorry. This should be cc. cb plus cc is negative. That means, yeah, that means that the integral over delta beta would be convergent on the real axis. But we're not integrating over the real axis. We're integrating over the imaginary axis. So that integral is also divergent. So we get another factor of minus I. So it's minus I squared. And so the integral defined in this way gives answer minus 1. And this was the conclusion that Juan came to in his paper using basically this way of defining that integral. So there are different reasonable looking ways of defining this integral that come to different conclusions. One piece of evidence in favor of this one is that if you try to study the flat space black hole, 4-dimensional flat space black hole, then the prescription 2a gives a positive density of states, and prescription 2b gives a negative density of states. So I think it's important to use 2a for cases with systems with negative specific heat. Okay, so the final part that I'm going to discuss is about this factor of I to the fourth. So first of all, what is the I to the fourth? The I to the fourth is multiplying these answers. And here I've, simplified I to the fourth to be 1. And, well, it's true as a mathematical fact that I to the fourth is 1. But it makes you a little uncomfortable. Like, maybe it came out real and positive because of a 1 in 4 coincidence. And so we'd like to understand the I to the fourth better. In general, there's no sharp way to trace the origin of the I to the fourth that I know of. Basically, there's infinity minus 4 negative modes, and it's not clear which the minus 4 are. However, you can do that in a kind of a limit where we take this gluing procedure, we glue 2 disks to make a sphere, and we move the gluing point very close to one or the other of the horizons. So let's move this gluing point very close to phi c by adjusting the value of the dilaton where we glue. And if we do that, then the integral over that tiny disk simplifies. And the important modes are kind of familiar from the Schwarzian theory. It's an integral over a wiggly boundary of this tiny little disk close to the horizon. And the action for those modes is this action here. Epsilon parameterizes the shape of this wiggly boundary. And n is a Fourier number. So for a normal black hole type horizon, this constant here is positive. And in that case, there's one negative mode, that's n equals 0. And that negative mode gets canceled by an explicit I in the measure, so we get a positive answer. For cosmic type horizon, this constant is negative. And so now, if we look at it, now most of the modes are negative. Most of them means infinity minus 3. There's the n equals 0 mode is positive, and the n equals 1 modes are not included. So for cosmic type horizon, there are infinity minus 3 modes, negative modes. And together with the I in the measure, we get I to the fourth. So I times minus I to infinity minus 3 is I to the fourth. So that's our best understanding of the origin of the I to the fourth, is it's related to the sign of this, this constant here. And that sign that sign arises because the de Sitter horizon is a maximum in space, which is directly related to this time advance behavior of shock waves. And it seems like there's probably more to understand related to that. Okay, so thank you very much, and I'll just leave this here for you to look at.
In the case where the black hole is marginally stable, you said that there is a zero mode that renders the partition function infinite. Do you have some thoughts about how to obtain a finite answer in this case?
Yeah, you just, I guess, so it's not that the partition function is infinite, it's just infinite in one loop approximation. So you need to go to higher order than that mode to get a finite answer.
Why would that change if you go to higher order?
Sorry?
Why would higher order change something in it?
Well, it's not exact zero mode. It's just that, like, it's a zero mode in one loop approximation.
But wouldn't that still kill the thing?
Kill what?
The particle, isn't it connected to like full loop order? It's some zero infinite at one loop order.
Yeah, so the path integral will not be infinite. It's only infinite in the one loop approximation. I'm not sure what you mean by killed. Is that dead or alive?
No.
It's like.
No, I was just wondering, like, did you say, like, I mean, it's cured by doing the two loop, like higher loops, or like cure something at higher loops if it was like it's subleading now?
Oh, well, think about an integral like e to the minus epsilon x squared minus x to the fourth. Like as epsilon goes to 0, then the one loop determinant diverges, but the integral is still convergent. Just you need to go to higher order, the x to the fourth term, to see that it's yeah. We haven't studied that. In a sense, it doesn't really matter because I think you should probably you could think about just fixing the mass of the black hole anyhow, as the observer could be compared to a black hole with some fixed mass, and then you wouldn't integrate over that variable at all.
In the option 2a, you give that eigenvalue either for z and z count. So is there any specific reason to look at z count?
Sorry, option 2a. Could you say it again? The
eigenvalue both for z and z count?
No, for z you get I cubed. Yeah, so for z we would have done the integral over beta on the real axis, and we would not have included this I here.
So since the beta integral is to get the density of state, should I do that integral last? Because I would first find the rest and then do that integral. So why is 2a more reasonable?
Well, okay. The previous literature actually said that, well, this I know of these like 5 papers on this, whatever, where I put and the papers that commented on the order explicitly say you should do the beta integral first, basically so that you impose the constraint, so that then the rest of the integrals make sense. So we can see that here, that the integral is conditionally convergent, and it's only convergent if you do the beta integral first. Now, you could say maybe the right answer is that it's supposed to be divergent, and then you need to do the Wick rotations and get -1. And the best argument I have against that is that you need to do 2a to get a positive density of states for the 4D Schwarzschild black hole. So I don't know. The answer I'm giving you is not very satisfying because it's a mixture of saying like these people said it in a paper and also it works in this one case, but it's an important case, so yeah. Why did we not say?
In the previous slide, like you had like gravity path integral with beta. So, like, here.
Yeah.
Why did you not divide?
Oh yeah, you could. Well, depends on exactly what you want to compute, but it's positive, so it doesn't matter whether you divide by beta or not. I mean, I'm not writing the integrand altogether, so yeah. Zhenbin made exactly the same point in the draft, and
You still did not divide by beta.
I still didn't write it because there's a lot of stuff writing here, and also I always get confused about whether we should or should not divide by beta. So.
If you take the limit as you go down the lukewarm curve towards empty de Sitter space,
Yeah.
Do you expect that limit to be discontinuous because you lose the object that was contributing to the negative modes, or is there some sense in which empty de Sitter ultimately also fits this story?
Yeah. Right. So in that limit, I guess you get close back to Wan's discussion with this probe particle, and well, right, but suppose the mass is not exactly zero, so it's yeah. Well, I guess the charge is quantized, so we could talk about charge 1. And, I mean, but I think, let me try to answer a version of your question that I think forgetting the charge is quantized, like, yeah, if the black hole becomes very light, then this returns to the, should return to the analysis that Wan did with this particle. And there, basically what happens is this, the contribution of the particle wrapping the geodesic is like not well separated from the rest of the integral. So it becomes harder to separate those pieces. And I'm not quite sure what you're supposed to say about that. We're not making a claim that empty de Sitter space has a positive density of states. And I think it's important to understand that further.
You mentioned that 2A is a phase of for class. Is this based on like a GR calculation, or is it like a tau integral?
Yeah, it's based on this. So the Schwarzschild flat space Schwarzschild black hole has one negative mode in the transverse traceless sector, and so the partition function is -I. But you can understand that as coming from the following integral: the integral over the area radius of the black hole of e to the minus the energy, that's like r plus r squared. And this integral is divergent and has to be Wick rotated. So the factor of -I we can see here. So this gives interpretation for the factor of -I in the flat space Schwarzschild black hole as saying that the integral over r is the saddle point is an unstable saddle point. But if you do the inverse Laplace transform before doing the integral over r, then it will just freeze the value of r. And then the integral will be positive. So that's the, yeah. It's very similar to the de Sitter case. The difference is that in the de Sitter case, you have an extra factor of I to the 4th.
Okay, we're running out of time, so let's thank Daniel again.